conclude the study of functions using knowledge of the first and second derivatives, uh, we'll go over two more examples of the most basic thing that initiated the discussion, namely the mean value theorem. Remember that the application of the mean value theorem led us to concluding that when a function has a positive derivative, where in any interval where the derivative of a function f is positive, then it's increasing, and if the derivative has a negative sign, then it's decreasing. There was a consequence of the MVT. For the same reason, where f double prime is positive, f prime is increasing, and therefore f is concave up. And f double prime being negative implies that f prime is decreasing, and therefore f as a function is concave down. Okay, so let's go back to the main theorem that allows us to conclude all of these things that we've been applying the last couple of videos. So, and the kind of problems again that we're asked to solve have to do with finding point that verifies the hypothesis of that verifies the conclusions of the MVT. So problem 1, verify the conclusion of the mean value theorem for the function f of x equals to x over x plus 2 on the interval 1, 4. Okay, so let's try not to forget what we have to do in this for this kind of problems. So what we need to find, C such that f prime at C is equal to the slope of the secant line joining 1 and 4 in the graph of f. Okay, so that means f of 4, because this is this point, this first point, the end point, 4 minus f of 1, 1 is the other endpoint, divided by 4 minus 1. Okay, so what is f of 4? 4 is f of 4 is 4 divided by 4 plus 2, and f of 1 is 1 divided by 1 plus 2. I'm just plugging in the values of x equals 4 and x equals 1 into this expression defining f. And now divide that by 4 minus 1, which is equal to 3. The first quotient is 4 over 6, or what is equal to 2/3. The second expression is 1/3. All of that is divided by 3. So we get 1/3 over 3, which is the same as 1/9. So we need to find a point C in the interval 1 to 4. C in the open interval 1, 4, such that the following happens: f prime C is equal to 1/9. And we need to find that point in between 1 and 4 because that's the conclusion of the theorem, that you're always able to find the point C in that interval whose slope, I mean, no, whose slope of the tangent line is equal to this difference quotient here, to correspond to the slope of the secant line. And this is what we're trying to accomplish here. So what is f prime of c? I mean, what is f prime of x in general? It's the derivative of x over x plus 2, so x over plus 2 prime, and this asks us to apply either the quotient rule or simplify things a little bit. So I know you already know the quotient rule and know how to apply it very well. So I'm just going to go over a shortcut, because this is the kind of example that appears quite often in exams. So I'm just simply gonna, I mean, this may save you a little bit of time. So instead of writing x here in the numerator, I'm writing x plus 2 minus 2. The 2's would cancel out until you get x over x plus 2. But the idea here is that if you split this into two fractions, you get x plus 2 minus 2 over x plus 2 prime. And the first expression is 1. The second expression is 2 over x plus 2. So this is much shorter than applying the quotient rule, because the derivative of 1 is 0, so you get 0. And 2 is just a constant, so you don't need to differentiate that, but apply, I mean, just take the derivative of 1 over x plus 2, which is minus 1 over x plus 2 squared times the derivative of x plus 2 with respect to x, which is 1. Right? All in all, this is 2 over x plus 2 squared. Okay, so what do we want to find? Here is a point x. Find a point C. Point C in 1, 4, such that 2 divided by c plus 2 squared is equal to 1 over 9, which implies then that the c plus 2 squared should be equal to 18, and this can happen if c is equal to the square root of a plus or minus the square root of 2 minus 2. So here we can discard minus square root of 18 minus 2, because this is outside 1, 4. Yeah, this number here is negative, so it's not 1, 4. However, c equal to the square root of 18 minus 2 is in the interval, lies in 1, 4. Now, if you're given a multiple choice question, immediately just go for this one, because it's the only possibility that you have. So don't even check anything. You know that the other one just cannot be, because it's a negative number. So if your computations are correct, this has to be the correct option. Okay. But now that we're solving this problem, let's go over. So let's try to show. We need to verify that this point is actually that this C is in the interval. So is square root of 18 minus 2 greater than 1? And is it less than 4? Okay, for the first inequality, this is the same as asking if 3 is less than the square root of 18. Which is true because 3 squared, this is true because 3 squared is less than square root of 18 squared, which is 18. Okay, and the second inequality is also true because this is equivalent to the square root of 18 being less than 6. And if you raise everything to the square, it gives you 18 is less than 36, so this is true. The square root of 18 minus 2 is in between 1 and 4. Okay, as I said, during the exam, maybe you don't have time to check that this belongs to the interval. Don't stress out. I mean, that's just a minor point, the analysis, because you know the theorem is true, right? And here you don't have any other candidate. You know that the other number you obtain here is a negative number, so that cannot possibly be the number predicted by the mean value theorem. So c equals square root of 18 minus 2 has to be the answer. Okay, and yeah. But if you want to check everything by hand, you can check that this is the point predicted by the theorem. So okay, let's go over one final example. One shorter example. Okay, so then same. So the same, but now for f of x equals e to the x minus x, and where the interval is now minus 1, comma 1. Okay, so the solution here. So what is? So we need to find c, such that f prime of c is equal to e to the 1 minus 1, which is the value of f at 1, minus e to the minus 1 minus minus 1. All that divided by 1 minus minus 1. So this is equal to e to the 1 minus 1 minus e to the minus 1. And now we'll have a plus minus and minus 1 divided by 2. So e to the 1. So e minus e to the minus 1 minus 2 divided by 2. So we need to find a point for which this is f prime is equal to e minus e to the minus 1 minus 2 divided by 2. What is f prime? F prime of x is equal to e to the x minus 1. E to the x minus 1. So where is this equal to e minus e to the minus 1 minus 2 over 2? So f prime, we want f prime of c to be equal to that. So e to the c minus 1 has to be equal to e minus e to the minus 1 minus 2 divided by 2. By 2, right? So this is what we want to solve. Okay. And then this implies that e to the c is equal to 1 plus e to the minus e to the minus 1 minus 2 divided by 2. Okay, I want e to the c to be equal to 1 plus this, which is the same as 2 plus e minus e to the minus 1 minus 2 divided by 2. 2's here cancel out, and we get e to the c. E to the c is equal to e minus e to the minus 1 divided by 2. And here we just take the natural log. So we get c on this side, and we get the natural log of e minus e to the minus 1 over 2. Alright, so this is, so this is the answer that we get. And as I said, I mean, we can do the same thing we did before, now simply using some the endpoints here to see that the c cannot be greater than 1. It has to be cannot be greater than 1. It cannot be smaller than minus 1. But since it's the only candidate that we obtain, it has to be the number predicted by the mean value theorem. So that concludes this section, the review of this section.